let's go ahead and do the exam solutions. So I just copied each of these questions directly from the exam. I don't think there were different versions, but if your numbers are different, it should be pretty much the same question. So the first 6 questions were all worth 2 points. Let's start. Okay, so it says state whether the set is open, closed, neither open nor closed. There is a possibility where it could be both, but it looks like we're not considering those. So what does this look like? This is going to be a square, right? It's going to look like this. Right, so the x coordinates are going to go from 1 all the way over here, x equals 2, and then from here we have y equals 1 up to y equals 2. Okay, so notice that the boundary of this set, right, where y is actually equal to 1 and where x is equal to 1, all of these points here on the boundary are not in my set. Okay, so this should be, this basically indicates that this is an open set. More technically, if I pick a point, because I can't pick a point on the boundary, I can zoom in close enough and draw a circle around it that is fully contained in this set. And I can do that for any point in my set, basically because there's no boundary. So this is going to be open. Is it closed? Well, to see if it's closed, can I find a sequence of points that converges to something that's not in my set? Well, if I just do a sequence of points going towards the boundary that converge to a point on the boundary, right? So all of these points here are in my set. Let me draw that a little bit better. So all of these points here, they're in my set and they converge, but the limit of these points is a point right here on the boundary. And that's that point that's there, that's not in my set. So this is not closed. Okay, so it's only open. All right, next question. So now we have the same thing, except now we actually also include the boundary. Okay, so here it's not going to be open, right? Because if I pick this point here, really any point on the boundary of this set, if I draw a circle around it, no matter how close I zoom in, this circle that I draw around it, or no matter how small I draw this circle, no matter it's never going to actually be fully contained inside of my set. There's always going to be a little part that's outside of my set. Okay, so since I can find a place where that happens, basically because it has a boundary, this set is not open. Okay, and now, is there a way to do a limit or a sequence of points that converge to something that's not in my set? So basically, I would need to have a sequence of points that converge to something out here. That's not going to be possible. Okay, so it's always going to converge to somewhere on the boundary. Right, basically this set contains its boundary, so it's going to be closed. All right. Next one. So we have set all of the values that x is strictly bigger than 1, y is bigger than or equal to 1, and y is bigger than or equal to 1, but the x is strictly less than 2, and the y is strictly less than 2. Okay, so here I can find a point where no matter what circle I draw around it, no matter how small, it's never fully contained inside of my set. So that means that since such a point exists, this is not an open set. Okay, so it's not open. Right? So basically, because it has some points on the boundary, that basically indicates that it's not going to be open. But over here, I can draw a sequence of points that converge basically to a point that would be on the boundary, but since there's no boundary on this side, right? It converges to something that's not in my set, so this is not closed. Okay, so basically since there's a portion where there's no boundary, it's not going to be closed. Okay, and since there's a portion that has a boundary, it's not going to be open. That's my answer. Okay, so state whether the point 0, 0 is an interior point of D, boundary point, or neither. Okay, so if it's neither, we would call it an exterior point. Basically means it's completely outside of my set. So let's draw this region. So this is the point. So this is a circle with radius 2. So I have a circle, speed dotted. Right, I have a circle with radius 2, but the boundary is not included here. And I'm excluding the center, right, because I can't have a radius of 0. Okay, so what is an interior point? An interior point means that if I draw a circle around this point, that everything in this circle is contained in my set. Actually, let me look at the correct answer real quick. Let's see, what did they put for the correct answer? This should be an interior point. Oh no, it's going to be a boundary point. That's okay. So this is going to be a boundary point. So first off, notice that this point here at 0, 0, it's not in my set. Okay. So since it's not in my set, it's not going to be an interior. It can't be an interior point at all. Okay, so an interior point is a point in my set where any circle I draw around it is also contained in the set. So this point right here, if I can kind of separate it off with a circle from everything out here, then it's an interior point. But it also requires that my point be in the set. Here, the 0, I can do that. I can draw a circle around it, and everything except that point is contained in my set. But 0, 0 is not in my set, so it's going to be either an interior point or a boundary point, or neither. So a boundary point is a point where so a boundary point is a point that is that's not in D, but any circle around it, right? Any circle around it intersects D. Okay, I'll say the ball circle around it with a radius r. Right, so the circle around this point intersects D. It is not empty. So all that's saying is that I can any circle that I draw around this point is going to intersect my set, meaning that it's going to be a point on the it's going to be a boundary point. Okay, so for example here, if I was to pick this point right here, any circle that I draw around this point is also going to intersect D. Okay, and it doesn't matter how small I draw the circle, it's always going to intersect D. Meaning that this point would be a boundary point. If I was to pick a point out here, if I zoom in close enough and I draw a circle small enough, I can draw a circle around it that doesn't intersect D, so this is not a boundary point. This would be neither. okay, so this is what they have in this case. So here we have the same setup. We have this kind of open circle with no point at 0, and it's asking about point 2, 0. So that's this point right here. So is this an interior point, boundary point, or neither? So again, here, if I draw a circle around this point, no matter how small I draw this circle, it's always going to intersect my set. It's always going to intersect my set D. Okay, so no matter how small the circle is, it always intersects D. This means that it's either an interior point or, well, this means it's a boundary point, is what that means. So this is going to be a boundary point. Okay, so I mean these definitions, like they sound technical, like what I'm describing, but really it's about as simple as it looks. It's just a way of actually describing what is the boundary of this set, what is the edge of this set. Okay, so it can be a little bit technical on how do we actually like technically define that, but the idea is the same, right? It's not actually in the set, but it's on the edge of the set, and here this is also in the edge of the set. Another one, okay. State whether the point 1, 0 is an interior. Okay, so same setup. And now we're looking at this point right here. So, since I can draw a circle around this that is fully contained in D, and the point itself is in D, this is going to be an interior point. Right, I can kind of circle it off and isolate it from the boundary, from the complement, so it's going to be an interior point. Okay, so all of those are worth 2 points, and I believe the rest are worth 10 points. I'll go back and check that at the end to see that that's correct. Okay, suppose that f is continuously differentiable and it gives us the gradient at 0. Find h prime of 0. So h prime of 0, I should probably find h prime of t first. That'll be easier. That's going to be, well, since it's the composition of these two, the chain rule tells me this is going to be the gradient of f at r of t dot r prime of t. So h prime of 0 is going to be gradient f at r of 0 dot r prime of 0. So r of 0 is 0, 0. That's the gradient at 0, 0. Dot r prime, that's going to be 1i plus 2t minus 5j. So r prime of 0, that's 1i minus 5j. So that's dot 1 minus 5. Okay, and then it tells us the gradient here. So this is going to be 2 minus 1 dot 1 minus 5, which equals 2 plus 5, which is 7. That's my answer. Okay, find the norm of the gradient at 3, 0. Okay, so we want to find the gradient of f, and f is equal to 1 over square root x squared plus r, plus y squared. Okay, so let's do the partial f with respect to x. So derivative of 1 over square root, let me just write this as x squared plus y squared to the negative 1/2. So it's going to be negative 1 over 2 x squared plus y squared to the 3/2. But I also need to multiply by the derivative of what's inside, right? This is the chain rule. So derivative of this inside part, actually, you know what? Let me just do this using the chain rule. This will be a lot easier. This will be a lot easier using the chain rule. So this is 1 over r, and then I know that r is square root x squared plus y squared. Okay, so df dx, that's going to be df dr dot dr dx. Okay, so this is negative 1 over r squared dot, so the derivative of this dr dx is going to be 1 over 2 root x squared plus y squared. And then I need to use the chain rule, right, under the derivative of this with respect to r, so times 2x, the 2's cancel, and I get, put that in here, x over x squared plus y squared. Okay. So this is r to the, this is r squared. That's going to be minus, let's put this in terms of, so we have minus x over x squared plus y squared root x squared plus y squared. So minus x over x squared plus y squared to the 3/2. Okay, so same thing, but we do the derivative with respect to y, and this is going to be exactly the same. dr dy, that's going to be y over square root x squared plus y squared. Okay, and df dr, let's see, do I want to go down? Not really. Okay, so df dy, that's df dr dot dr dy. This is going to be exactly the same thing. So this is going to be negative y over x squared plus y squared to the 3/2. Right, because df dr, that's the same in both cases. So that's going to translate the same as this. And dr dy, right, this is exactly the same thing. It's just with y instead of x. So it's going to be the same. Okay, so what is the question asking? The question asks, so the gradient at 3, 0. So I need each of these evaluated at the point 3, 0. So here I plug in 3 and I get df dx at point 3, 0 is going to be minus 3 over 3 squared to the 3/2, which is going to be negative 1 over 9. Right, that's 3 over 27. Yeah. Okay, and here this is just going to be 0. Okay, so the gradient at the point 3, 0 is going to be the vector negative 1 over 9, 0. So the norm of the gradient at f is going to be square root of 1 over 9 squared plus 0 squared, which is 1 over 9. let's see if that's the same answer they have. Yeah, so 0.1/9, if you plug that into a calculator, you get 0.11111. Right, so you round that off to 2 decimal places, you get 0.11. Okay, next question. Okay, state whether f has a local minimum, maximum, or settle point at 0, 0. And it tells us that it's a stationary point. Okay, so here we're going to need the matrix of second derivatives. Okay, so if you recall, this was called the Hessian matrix. So this is the matrix df squared dx squared d squared f dy squared df squared f dy x dy and d squared f dy dx. So remember, these two things on the off diagonals are going to be the same. Okay, so to compute these, I should first compute the gradient, so I have the derivatives. It's going to be 2x plus x, and this is going to be 4y plus x, and this should be plus y on top. Okay, and then so the Hessian, and notice real quick, I can't plug in 0, 0, because then this would be a constant, and then I can't take the derivative of that. So I need to take the derivatives first. So the second derivative with respect to x, so that's the derivative of this first component with respect to x, this is going to be just 2, right? Y is a constant, derivative of this with respect to x is 2. Okay, so then I do the derivative of this with respect to y, and that's going to give me 1. And I know that these two are going to be the same, so this is also going to be 1. And then I need the derivative of this one with respect to y, so derivative of this, the y component, the y derivative, with respect to y, that's going to be 4. Okay, so to determine whether it's a local minimum, maximum, or settle point, I'm interested in the determinant of h. So that's going to be 2 times 4 minus 1 times 1, which is 8 minus 1, that's 7, which specifically is bigger than 0. Okay, so that rules out settle point. So it's either a local minimum or a local maximum. So now I look at just the diagonal ones. Okay, so technically I should look at the sum and whether they add up to 0 or add up to something positive or add up to something negative. But the textbook only says to just check that one, and that's enough. And it is enough. So in this case, it's positive. So this right here tells us max or min. So since d squared f dx squared is bigger than 0, this tells us that it's a local minimum. Okay. There we go. Okay, so a very similar question. So we'll do the same thing. First, I'll compute the gradient. Oh, actually, let me make one point quick on this previous one. Notice that this h didn't depend on what position I was in. Okay, So as long as I have a stationary point, any stationary point, it's going to be a local minimum. Okay. So in normal cases, this is going to depend on my choice of what point I'm at. Okay, so this is going to be 2x plus 5y, and then the gradient of this is going to be 4y plus 5x. Okay, so the Hessian matrix, this is going to be d squared f dx squared, d squared f dy dx, d squared f dx dy. I think I did those backwards. It doesn't matter, they're going to be the same value. Okay, so the derivative of the x derivative with respect to x is going to be 2. This is going to be 5. 5 because they have to be the same. And the derivative of this with respect to y, of this with respect to y, that's going to be 4. Okay, so the determinant of h is going to be 2 times 4 minus 5 times 5. This is going to be, that's 8 minus 25 minus 17. Doesn't matter, it's going to be less than 0. And because it's less than 0, this tells me right away that this is a saddle point. I don't have to do any extra check. If it's less than 0, it's a saddle point, I'm done. Okay, find the value of y, the positive value of y, such that there is a point xy on the hyperbola here that is closest to... Okay, so this looks like it's going to be a Lagrange multiplier question. We want to find the point xy that is closest to this, that is still on this, and it looks like we're going to have more than one value, so it asks us for the one with the positive y component. Okay, so what do we want to minimize? We want to minimize so our objective function. So what is it we want to minimize? We want to minimize the distance from xy to the point 0, 4. Plus y minus 4. Okay, so we want to minimize this given the constraint that g of xy is equal to x squared minus y squared. So the constraint is that g of xy equals 1. Okay, so we're going to use the Lagrange multiplier method, which, if you remember, means that we introduce an additional variable like this. Okay, so trying this again, we have that the function we want to find the point that's closest to the point 0, 4. Right. Look at this. We want the point that's closest to 0, 4. So the function we want to minimize is square root x minus 0 squared plus y minus 4 squared. But we have the constraint that it has to satisfy x squared minus y squared equals 1. So we have this constraint, x squared minus y squared, and that has to be equal to 1. Okay, so we use Lagrange multipliers. So we have that the gradient of f equals lambda times the gradient of g. So we compute the gradient of each of these. Let me rewrite this. This is going to be x squared plus y minus 4 squared Okay, so the partial of f with respect to x, this is going to be, so I do the square root, that's going to be 1 over 2 root whatever I have in here, times the derivative of what's on the inside with respect to x, that's going to be 2x. So these cancel out. And I do the same thing for, that's where my mistake was. Yeah, that's where it was. Okay, so I do the same thing with respect to y, and I get 1 over, so this part's going to be the same. And here's where my mistake was. When I do the chain rule, I don't get 2y, I get 2 times y minus 4. There you go. So those cancel, and I get y minus 4 over, that's much better. Okay, so the gradient over here, let me just finish that up. So the gradient of f is going to be x over x squared plus y minus 4 squared, and then y minus 4 over square root x squared plus y minus 4 squared. That's the gradient. Okay, so the gradient of g is going to be the same though. So let's draw a line. That's going to be 2x minus 2y. So this gives me the three equations. So I set the x components equal with this extra lambda. So I have x, I'll remember 1, x over square root x squared plus y minus 4 squared equals 2x lambda. Equation number 2, I have y minus 4 over this whole mess equals minus 2 lambda. And then I still have the constraint. Nope, not plus, that's minus. Okay. So what I'm going to do first is I'm going to solve for lambda. So I have, so I cancel x on both sides. I get lambda equals 1 over 2 root x squared plus y minus 4 squared. Now I take that lambda and I plug it in down here. There should be a y right here. So I plug that in here and I get y minus 4 over this thing I have to keep writing every time equals minus 2y over 2 root x squared plus y minus 4 squared. Okay, so the 2's cancel, these cancel on both sides, and I'm left with y minus 4 equals minus y. So if I rearrange this, I have 2y equals 4 and y equals 2. So if I take this and I plug it into the constraint, okay, this tells me, so I take that and I plug it in here. This gives me what? This gives me x squared minus 4 equals 1, so x equals plus or minus square root 5. So that gives me the points root 5, 2, and minus root 5, 2. Okay, so now I need to do this again. Let me copy this down. But I need to do the same thing except I solve the second equation first. And then I'll check for lambda, and then I'll check which one of those gives me Okay, so right, I have these equations. So now I'm going to take this and I solve for lambda. Okay, so this gives me lambda equals y minus 4 over 2, so minus plus 2y root x squared plus y minus 4 squared. And I take that and I substitute it back in here, which gives me x over x squared plus y minus 4 squared equals 2x lambda, which is minus y plus 4 over 2y root x squared plus y minus 4 squared. So that cancels on that side. This cancels here. The x's cancel. And if I multiply both sides by y, I have y equals minus y plus 4. And this is actually the same thing I had as before, right? Y equals 2. And that gives me, again, y equals plus or minus root x. Oh, sorry, root 5. So sometimes I can get the same values depending on how I do this. Sometimes it gives me different points. That's fine. But yeah, so to answer the question is, let's go back to attempt number 1. Find the y value, okay? And in all of these, we saw that the y value was just 2. So y equals 2 is my answer. Okay. Oops, that's so next question. So find the maximum directional derivative of the function. Here. Okay, so the maximum directional derivative that's going to be, so we know that the direction that this is maximum in is in the direction of the gradient, okay? So to find the maximum directional derivative, we know that we want the direction vector, d, to be the gradient. But remember, we need to normalize it, so d hat, I need to normalize it. Okay, so I need to compute this. Well, actually I don't need to yet. Because now, if I do, what is the directional derivative in this direction? That's going to be the gradient of f dot d hat. This is gradient of f dot grad f. This. And like you've seen in several reviews, this is norm gradient of f squared over gradient of f. That cancels. So the maximum directional derivative is going to be in the direction of the gradient, and the magnitude of that directional derivative is just going to be the norm of the gradient. So I just need to compute the gradient, and that's all. So this is going to be, sine is cosine, so it's going to be 3 cosine 3x minus 4y, and here's going to be minus 4 cosine 3x minus 4y. So the gradient at the point 0, 0. So that's cosine of 0, it's going to be 3, and that's going to be minus 4. Okay, so the norm at this point is going to be square root of 3 squared plus 4 squared, right? So that's a 3, 4, 5 triangle, so this is going to be 5. And that's my answer. Okay. Find the directional derivative of the same function at the point 0, 0 in the direction of this. Okay, so we need to check that that's a unit vector, and if not, we need to convert it to a unit vector. It is a unit vector, right? So this is 3 over 5, and this is 4 over 5. Okay, so that's going to be, we'll see that in a second, it's going to be a unit vector. I'm just putting that to remind myself. Okay, so find the directional derivative. So the direction is going to be 3/5, 4/5, and we can check that this is a unit vector, right? The norm of this is 3 squared over 5 squared plus 4 over 5 squared. That's going to be 9 plus 16 over 25. Right, so that's 25 over 25, which is 1. Right, so this vector has a norm of 1, so it's a unit vector. So the directional derivative we want is gradient of f at 0, 0 dot our direction vector, right, this one over here. So the gradient of f is, we did this already, it's going to be 3 minus 4. And we want to do the directional derivative of this in this direction, so gradient of f dot d hat is going to be 3 minus 4 dot 3/5, 4/5, which is equal to 9/5 minus 16/5. So if I do the subtraction, that's going to give me what? Minus 7 over 5. I don't have a calculator next to me. Actually, no, yes I do. Equals so negative 1.4. Let's make sure that that's correct. Negative 1.4, yes. Okay, next question. Given the surface, basically find the tangent plane. Okay, so find this component of the tangent plane. So if you remember though, this is going to be, these are the components of the gradient of this function on the right hand side. Well, this is an equation. But if we say that g of x, y, z equals xz squared plus 2y squared, right, the gradient of this function is going to be the normal vector for the tangent plane. Okay, so that means that these are going to be the components of the normal vector. These can be the components of this function, of the gradient of this function. Okay, so the gradient of g, we'll need to do this at the point 1, 2, 3, but the gradient of g is going to be, this is going to be z squared, 4y, and 2xz. Okay, so gradient of g at 1, 2, 3 is going to be, that's going to be 9, 8, and 6. Okay, so we know this lines up, right? The 6 lines up with the 6. We're on the right path. So A is going to be equal to 9. And that's my answer. Okay, so if I do the same thing Is this the same function? I think it's the same function. X z squared 2y squared. X z squared 2y squared, yeah. So it's the same function, except now it asks for b. So I can reuse the same answer because I already computed this. B is going to be the second component. That's going to be the 8. So I have b equals 8. Right, because I have the gradient of g at 1, 2, 3 was equal to 986. Okay. Getting close to the end. Scalar parametric for the normal equation through the line. Okay, so this one, again, it uses the same function. Yeah, it uses the same function, but now it wants the normal line through that point. And we write the parametric equations this way. Okay, so if you remember, these are the components of the direction vector. Right? These are the components of the direction vector for this line. And for us, the direction vector of this line is going to be the gradient of this function at this point. Okay, so the direction vector is going to be, we already did this computation. It's the gradient of g at 1, 2, 3, which is 9, 8, 6. Okay, so find a, that's the same thing. So I just want to point out real quick, here the gradient represents something very different than in the other problems. Right here the gradient is representing the direction vector of our line, whereas in the previous ones it was representing the normal vector of the plane. Okay, and those are not the same thing. So if I'm not mistaken, the next question is also going to ask for b. Yeah, so same computation, right? It's just 8 now, so we do b equals 8. Okay, and that's the end of the test.